Hello everyone. In this tutorial, we're going to take the assembly program example we went over in the previous video and see how the following updates after each instruction, which are the program counter, accumulator A, accumulator B. When we have the square bracket, that means the content at memory address 1000, and then we're going to see how we can obtain the following flags, N, Z, V, and C. So the program counter always points to the next instruction to be executed. So in the initial state, the program counter is pointing to 2000, which is this instruction here. So the program counter will be 2000 initially, or pointing to memory address 2000. We don't know the content of accumulator A, we don't know the content of accumulator B. The content at 1000, we initialize it to 0. So this will be 0. Then we can write it 00 in hex. The flags, we don't know the status of the flags, so I'm gonna just like put unknown. And then the stack pointer is always pointing to the top of the stack. So the top of the stack, since we started fetching at memory address 2000, so this will be the top of the stack. So the next instruction is LDS 2000. So at this instruction, the program counter will be pointing to the next one. So let's go back to what we did in the previous video. So we start at LDS, it takes 3 locations in memory, 2000, 2001, and 2002. So the next instruction starts at 2003. So the program counter here will be pointing to memory address 2003. And then when we execute LDS, we're not loading anything to accumulator A. So also this one will be unknown, unknown. The content at 1000, it's still 0. And then let's see the flags from the instruction LDS 2000. So let's go back to our instruction glossary and search on LDS. So we see the negative flag, Z flag, they have a value of delta. What delta means? Delta means those flags get affected when we execute the LDS instruction. The V flag will be cleared when we execute LDS, and the C flag, it has the dash. So at the top of the instruction glossary, you see what those delta means. The delta means the status bit affected by the operation, and then the dash, the status bit is not affected by the operation. So let's go back to our LDS. So basically the two flags that we need to figure out are the N and the Z flag, and then we can fill the V and the C flags. So going back here, from LDS, the V flag will be cleared, and then the C flag will be carried from the previous instruction, but we don't know it, so I'm just gonna put a dash, and the stack pointer is always pointing to the top of the stack. So this will be 2000 all the way. We're not gonna worry about it. And then let's see the negative flag. The negative flag is set when we execute the instruction and we get a negative value. So from the LDS 2000, we did not get a 0 value, we did not get a negative value, so those will be zeros. So the next instruction, LDAA 25. So we're loading 25 in accumulator A, but first let's see the program counter will be pointing to the next instruction. So after 2003, we had 2005. So the program counter here will be pointing to memory address 2005. The content in accumulator A will be 25 in hex. B, we don't know. The content at 1000 will be 0. And then now let's go to our instruction glossary and see which flags get affected by LDAA. So in LDAA, also the N and the C flags gets updated or gets affected. The V is 0, the C is carried from the previous instruction. So first the V is 0, C is unchanged. So those means they're the same, so you don't confuse with 1. So let's see the negative flag. Obviously 25 is not negative, and then you can convert it to binary. So the 25 and binary will be 2 will be 0, 0, 1, 0, and then 5 will be 0, 1, 0, 1. Because in 4 bits you have 8, 4, 2, and 1. So to make 5, you set these 2 bits to 1. So the most significant bit is 0, so this is not negative. So the negative flag will be 0, will not be set. The Z flag will be 0 because the result from this instruction is not 0. So let's move to the next one, add 34 to accumulator A. So the stack pointer will be pointing to the next instruction. So after 2005, we have 2007. I think I said the stack pointer, the program counter will be pointing to 2007. And then we're gonna add 34 to 25. So let's do it in binary. We know this is 59, but in binary, we can figure out the flags. So 34 will be 00, 3 will be 0011, and then 4 will be 0100. If we add them in binary, we get 1001, 1101, 10. So that's 59 in hex. So the accumulator A will have a value of 59. B is unknown. The content at 1000 is still 0. And now from ADDA, let's see which flags get affected. So we go to the instruction glossary, we search for ADDA. ADDA, all the flags get affected, N, Z, V, and C. So let's go back and try to figure out those flags. So from this instruction, the most significant bit is 0. So that means this is not a negative number. So this flag will be 0. The 0 flag, we did not get 0 from this instruction, so this will be 0. So the overflow flag, we added two 8-bit numbers and we got 8-bit number. Also, we need to look, we added two positive numbers because the most significant bit is 0, 0. And then we got a positive number. So the V flag will be 0 at this instruction. And then the carry flag, we didn't get any carry out, so this will be 0 as well. So let's move to the next instruction, add 11 to accumulator A. So first, the program counter will be pointing to the next instruction. So after 2007, we have 2009. So this will be here 2009. So we're adding 11 to 59, so that's 11. And hex will be equal to, in binary, 1 is 0001, 0001 again, and then let's add them. 1 plus 1 is 0 with carry 1. 1 plus 1, 1 plus 0 plus 0 is 1. 0 plus 0 is 0, so we're adding these two. 1 plus 0 is 1. 1 plus 1 is 0 with carry 1. We get 1 here, 1, and 0. So if we convert this to hexadecimal, so from these 4 bits, let's start with these to the left, 0, 1, 1, 0. 4 plus 2 is 6. And then 1, 0, 1, 0 is 8 plus 2, 10. 10 is A in hexadecimal. So the content in accumulator A will be 6A. B is unknown. The content at 1000 is still 0. And then now we're going to look at in ADDA, we know all the flags get affected. So this the negative flag, this is not negative because the most significant bit is 0. So it will be 0. The 0 flag is 0 because the result is not 0. Now we're going to see the V flag. Also, we added two positive numbers. We got positive number. We added two 8-bit numbers. We got 8-bit numbers. So this will be 0. The carry, we don't have any carry out, so this will be 0 as well. Now let's see the next instruction, add 18 to accumulator A. So now we're going to take 6A, which is 0, 1, 1, 0, 1, 0, 1, 0 in binary, and then we're going to add 18. 18 in hexadecimal is 12. So, and then 12 in binary, the 1 is 0, 0, 0, 1, and then the 2 is 0, 0, 1, 0. So 0 plus 0 is 0. 1 plus 1 is 0 with carry 1. We have 1, 1, 1, 1, 1, and 0. So this one in hexadecimal will be 4 plus 2, 6 plus 1 is 7. And then 1, 1, 0, 0 will be 8 plus 4 is 12. 12 in hexadecimal is C. So the accumulator A will be 7C. And then the program counter will be pointing to the next instruction. So after 2009, we have 2000B. B is still unknown. The content at 1000 is 0. And then from ADDA, all the flags get affected. So first, the most significant bit is 0. So that means the negative flag is 0. The Z flag, we didn't get 0 for the result, so this will be 0. The V flag, we added 2 positive numbers. We got positive number, and then we got 8-bit. So those will be 0, and then no carry out will be 0 as well. So let's see the next instruction. Add this binary number to accumulator A. So first, the program counter will be pointing to the next one. After 2000B, we have 2000D. So the stack pointer at this instruction will be pointing to the next one, which is 2000D. And then accumulator A will add, it had 7C from the previous instruction, which is we have it here in binary 0111, 1100. And then this binary number, let's add it as it is. So 0000, 1110. So if we add them, we have 0, 1, 0 with carry 1, 1 with carry 1, 0 with carry 1, 0 with carry 1 again, 0 with carry 1, and then 1. So this one in hexadecimal will be 8. And then these 4 bits we have 8 plus 2, 10. 10 is A. So the accumulator A will have a value 8A in hexadecimal. B is unknown. Content at 1000 still 0. And now let's see the flags. So now here the most significant bit is 1. So that means this is a negative number. So the negative flag will be 1. The Z flag, this value obviously is not 0. So this will be 0. The Z flag, the V flag, sorry. So we added 2 positive numbers because the most significant bit here is 0. Most significant bit is 0. But we got a negative number. So this is not possible to add 2 positive and get negative. So the V flag will be set. The carry flag, we don't have any carry out. So we added 2 8-bits. We got an 8-bit. So this will be 0. So next, to store the result in sum. So let's see the program counter. So after this instruction, so after 2000F, if we increment it by 1, the next memory address will be 2010. So the program counter will be pointing to 2010, and then we're storing, we're not changing the accumulator A, so this will be 8A, B is unknown. Now the content at 1000 will be 8A. This will get updated after this instruction because we're storing a value in accumulator A at sum. Sum was at memory address 1000. And then now let's see the flags. So from STAA, let's go to our instruction glossary and see what flags gets affected. So STAA, we have the negative and the 0 flags get affected. So let's go back. The V flag will be set, will be reset to 0 or cleared, and the C will be unchanged. So let's start with V. Since this will be cleared, will be 0. The C flag will be unchanged, so it was 0, it will remain 0. How about the negative flag? 8A is negative because we have the most significant bit is 1, so this will be 1. How about the 0 flag? We did not get a 0 value, so this will be 0. So this is how we can figure out the flags, the content of accumulators, the content at memory address 1000, and then the program counter. I hope this tutorial was helpful. Thanks for watching.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.